Hello to everyone joining. This is Chegg's Gen Chem Office Hour. We are live every Monday, same place, same time, 8:30 p.m. Eastern Time. There are tons of office hours all week long. Hopefully, you've already checked some of those out. And we're just going to keep doing this. Goal is to help as many students as possible. So more people can find these office hours. All right, let's get started. So with this one, this was a question that was asked last week. The decomposition of N2O5 to NO2 and O2 is a first order reaction. At 60 degrees, the rate constant is 2.8 times 10 to the negative third inverse minutes. If the initial pressure of our reactant is 125 kilopascals, how long will it take for the total pressure to reach 164 kilopascals? So right away, you look at this and you're overwhelmed because it is such a wordy problem. And that's what's really tricky about equilibrium sometimes, right? It's just deciding where do I even start? So let's actually just underline the information that's important in this. And then let's circle what we're trying to figure out. How long? Okay, if we look back at our rate constant, how many minutes is that going to take? All right, but we need to back up. So in this problem, we're given the word problem, but we don't actually have the chemical equation. So let's start with that. So I'm going to write out the chemical equation. Anytime you're writing out an equation, just like with any other topic in chemistry, you want to make sure it's balanced. So we have the decomposition of N2O5. So break down that word, right? A decomposition reaction, we are breaking a reactant down into multiple products. In this case, we have two products. So we have NO2 and O2. And the cool thing about these Gen Chem sessions is if you have not done this topic yet, I will talk through other topics related to what you might be studying in class as well. So for example, if you are naming molecular compounds right now, we can go through and we can name all of these. We have N2O5, 2 atoms of nitrogen. This is going to be dinitrogen pentoxide. This one only has 1 atom of nitrogen for those 2 atoms of oxygen. That's going to be nitrogen dioxide, right? And this is just oxygen gas. So cool thing about these sessions, start putting those questions in the chat as I'm going through this first question. All right, let's go ahead and balance this decomposition reaction. One of my balancing tricks is just start with the element that has the largest subscript. So which element do we have the most of? Although oxygen is in 3 places here, so let's scrap that. And if you notice that one element is in every single one of your reactants and products, save it for last. So in that case, I'm going to look at the nitrogen. I see I have 2 nitrogen atoms on this side, only 1 on that side. I'm going to go ahead and put a 2 here. So now that my nitrogen is balanced, I'm also going to have to balance my oxygen. I have 2 times 2, that's 4 plus 2 gives me 6 right now, versus I have 5 here. So if I change that, if I just had like 1/2 of this, then it would be balanced, right? Can I really have half of a molecule? No, that bothers me. So I'm going to go ahead and balance this just by multiplying everything in this reaction by 2. All right, let's double check. I have 4 atoms of nitrogen, 4 atoms of nitrogen. That looks good. I have 10 atoms of oxygen on my reactant side. I have 8 plus 2. That also gives me 10. So now it's balanced. All right, so back to the question. And I had someone on YouTube. Yeah, put that question in the chat. That's what I'll answer next. All right, so back to this question. I now have a balanced reaction. How am I even going to figure out the total time? I need to use a rice table. So here's my reaction. So I am going to be writing out the equilibrium expression using this rice table. We don't have an easy 1-to-1 ratio, so it does help to actually take the time to do this. So I know my initial pressure is 125 kilopascals. I'm going to assume that I don't have any of my products initially because we're looking at the decomposition of the dinitrogen pentoxide. So what's going to happen? I'm going to subtract 2x from that initial pressure. I'm going to add 4x and just x to O2. So again, what you are adding and subtracting is just based on those coefficients in that balanced equation. So now this is going to end up being 125 minus 2x, 4x, and x. So with these rice tables, they look really intimidating. You have your initial quantity or your initial pressure, in this case, not concentration, your change, and then equilibrium. So you can set this up. I like to just draw the line so it looks like a simple subtraction or addition problem, right? To find those answers. All right, so now we have all of our equilibrium pressures, right? This is what it's all going to be equal to. We know our total pressure at equilibrium is 164 kilopascals. So what I'm going to do is I'm going to add up all of these to equal 164. So I have 125 minus 2x plus 4x plus x equals 164 kilopascals. All right, just going to do some quick algebra here. So I have 5x minus 2x, that gives me 3x. So I have 125 minus 3x equals 164. Sorry, plus 3x equals 164. So now all I have to do is just do some rearranging. I subtract 125, I divide by 3, and I get x is equal to 13. All right, so now I can use that. And you're like, wait, okay, why do we just do that, right? The goal is to figure out how long it's going to take for us to reach this point where the total pressure is 164 kilopascals. So far what we have done is we have solved for x. This is important because I want to figure out what my final pressure of that N2O5 is. Why? Because this is a first order reaction with respect to that single reactant, right? So the whole rate is going to be based on this. So I'm going to use the rate law to then solve for the time using my rate constant. All right, so let's just figure out what that's going to be. 125 minus 2 times 13, that's 26. This is going to be equal to 99 kPa. All right, so what have we found out so far? We know our pressure at equilibrium, or our final pressure rather, is 99 kilopascals. All right, I've run out of room, so I'm going to go ahead and clear the board. And if you have questions on this so far, please put them in the chat so I have an idea of where to go from here. All right. So again, we are just trying to solve for the amount of time it would take for the system, the pressure to increase from 125 to 164. All right, so now I'm going to use this fact that it's a first order reaction. There aren't too many things you have to memorize in chemistry. These rate laws, and it does help to have these memorized. So let's go ahead and do that. So for the first order reaction, I'm going to end up having the log of my pressure final over my initial pressure is equal to negative KT, where K is that rate constant, right? Which thankfully we're given in this problem. So if we want to just solve for T, we're going to substitute everything in. So we're going to take the natural log of my final pressure, which was 99 kilopascals, divided by my initial, which was 125. All of that is equal to our negative rate constant, 2.8 times 10 to the negative third inverse minutes times time. All right, so then all we have to do is just rearrange this, take that natural log, divide by your negative rate constant to figure out how many minutes that would take. And I think it's like 83. Give me a second. You double check it too. I feel like the hardest part of doing some of these problems sometimes is just finding your log buttons on the calculator. Same with like pH and pOH calculations, right? You got to know where that is, but it's not too often that you have to worry about it. Yeah, all right, so this would take 83.2835 minutes. How do I know it's in minutes? I'm going to use my constant that I'm given. That's going to give me my time. It might be seconds, but in this case, we were given in minutes. So that's what we're going to use for this time. Because if I had written out all of my units, and if you think about it, if I divide by inverse minutes, it is going to end up being the opposite. So that's going to end up with minutes. Last thing I need to do is just double check those sig figs. Technically, we're going to go with, this one only had one sig fig, but since this one had two, and since it's just a problem put in the chat, likely it has 2 sig figs total. This is probably 83 minutes. All right, so just a little bit about rate laws. Again, this was a first order reaction. So we had to take all of this information, synthesize that, right? We wrote out the balanced equation. We then went through an ice table to figure out our equilibrium pressures. From there, I could solve for my final pressure of N2O5, because again, this reaction was first order with respect to the pressure of N2O5. So from there, I can then use that, substitute everything in to solve for the amount of time it would take to get to that point. All right, let me hop in the chat, see kind of where you guys are at. Please keep putting those questions in the chat. Goal of these sessions is to help as many students as possible. Chegg is here to help you out. They just released this really cool new feature. I don't know when they released it, but I just saw it this week, where they actually have built-in practice problems now. So let's say you are struggling with equilibrium. Guess what? Many people are struggling with equilibrium right now. All you have to do is just type into their practice, and they will generate 10 practice questions for you with hints, with answers, and with explanations. How cool is that? They're making this whole process of studying and learning chemistry and all of the other subjects too It's not like Chegg is just limited to chemistry. They're just making your life so much easier. So if you have not checked them out, you definitely need to. All right, so that was a little bit on rate laws. I think I saw equilibrium in the chat. Let me check. Yeah, so someone said on TikTok, thermochemistry is the hardest AP Chem unit for me. Acids and bases and equilibrium are my faves. You were in the, the minority there. Thermochem is hard. You have a lot of constants and equations and things like that to keep track of. My recommendation for thermo is use the units to your advantage. So definitely like check your work based on the units. Use your constants to make sure that everything else matches up, and use that to kind of figure out which equation you need to use, and that will help. With thermal, sometimes just the signs are the hardest part, right? Understanding whether heat is lost or gained. And the more practice you get and the more you're exposed to all those types of calculations, easier it's going to be. And again, the goal of these sessions is just to help as many students as possible. So let me know what you want to practice and we will go through it. And no question is too easy or too hard, as long as it's Gen Chem based. If you're looking for orgo help, know that there's another session tomorrow night that's just devoted to organic. All right, so let's just talk molarity. So when we're thinking about solution concentrations, these are the equations you need to know, right? The molarity, or the concentration. So basically, molarity is just a way to measure concentration. It's the moles of solute dissolved per liters of total solution. Some other equations you might need if you're doing a dilution, you might use this equation. M1V1 equals M2V2. So if you think about a solution and you are diluting it, you have a 6 molar, you have, I don't know, 100 milliliters of 6 molar hydrochloric acid. You want to dilute it down to 3 molar. You're going to add water to it to make that happen, right? When you add water, are you changing the amount of the solute or the amount of hydrochloric acid in that solution? No, you're just diluting it. So we're not changing the moles at all. So what we can do is we can say, okay, our initial volume times our initial concentration is going to be equal to our new concentration times our new volume, because basically the moles have not changed. So we can write those two equations and set those up so that they are equal to each other. When you're doing concentrations, there are also other types of concentrations that you'll have to figure out, right? Like molality. So with molality, we're still looking at moles of solute, but instead we're looking per kilograms of solvent. So there's mole fraction, all of those, and that's what makes this kind of tricky, right? Just trying to figure that out. All right. Let's see, I think I had a request for thermo, so let's go ahead and do some thermo. I didn't really have any thermo questions. That was like one of the topics I did not have prepped for tonight, but we can just make something up and go. All right, we'll do a delta G calculation. We'll just talk through that. All right, let's do something with nitrous oxide. All right, so let's calculate delta G at 290 Kelvin, given a delta S value of negative 150 and a delta H of negative 120 kilojoules. All right, so let's say you're doing some thermo. Half the battle with thermo, right, is keeping track of all the different equations. For the most part, when you're calculating delta S, delta H, and delta G, it's always products minus reactants. Keep in mind that's going to change if you're looking at the energy associated with bonds breaking and forming. So if you're looking at the enthalpy of the reaction, it's always going to be the energy of the reactants minus the product. So it's a little bit different, but that's the only exception. All right, so with this, we are trying to find delta G. we're given our delta S and our delta H, which is really nice. So you don't have to use the tables to then calculate that. But again, like I said, if you weren't given that information, you just pull each of these, you pull that value from the table and just subtract the energy of the product minus that of the reactants. All right, so because we're looking for delta G, the Gibbs free energy, delta G is equal to delta H minus T delta S. All right, so with this, you want to make sure all of your units match up. Right away, I'm noticing I have the difference. Entropy is typically given in joules and enthalpy is given in kilojoules. So just make sure to switch one or the other. I typically switch this one into kilojoules, but it doesn't really matter as long as everything else matches up. So you just want to make sure everything matches up. Your temperature, in this case, it's given in Kelvin already, so I don't have to do that conversion. That makes it a little bit easier. So we're just going to go ahead and substitute that in. So delta G is equal to delta H, which was negative 120 kilojoules, minus T, which was 290 Kelvin, times our delta S. Again, I'm going to convert that into kilojoules right away. So I'm going to divide that by 1,000. All right, so a quick trick with that, if you're dividing by 1,000, you're just going to move your decimal over 3 places to the left. So that's just going to be 0.150 kilojoules per Kelvin. Be careful, you don't want to lose your sign here because that's going to make a big difference if you're trying to figure out whether or not this is a thermodynamically favorable process. All right, so let's plug this in, figure out what this is. So negative 76.5. All right, and what are my units here? So if I have, it's going to be kilojoules per Kelvin, right? Wrong. So look at this. Kelvin times 1 over Kelvin is going to cancel out. This is just going to be negative 76.5 kilojoules. All right, with Gibbs free energy, why do we care about this? We want to figure out whether or not this is a thermodynamically favorable process, right? So if it's thermodynamically favorable, we're going to have a negative delta G value. Understand, though, that even if you have a negative delta G, that doesn't necessarily mean this reaction is actually going to happen. You can also have something that's under kinetic control, which just means that even though, yes, everything is telling you these conditions are favorable, the reaction is proceeding so slowly that it looks like nothing's happening. So just know that that can happen too. So even if you have a negative delta G, doesn't guarantee a fast reaction. All right, I don't know if that was helpful on TikTok. Oh, it looks like I have a lot more questions that I totally missed. All right, thank you all. All right, let's see. Let me hop back in the chat and catch up. Thank you guys for being here tonight. I hope this is helpful. The goal of this session is just to help as many students as possible. So thanks for being here tonight on this holiday. Hopefully everyone had some time off today or just had a good time to, I don't know. I feel like we're hitting the part of the semester already where everyone's ready for spring break, right? Like a long weekend was much needed after the last couple of weeks. We will make it though. We're getting close. Does anyone have spring break? Like first week in March? 2 weeks away? We have a late spring break here, so we still have to wait until April, but we'll survive. We'll be okay. All right, let's see. So I had a cool question on YouTube. If ammonia was used as aviation fuel, would its reactivity cause it to dissipate in the atmosphere? That's a really cool question. I don't know if ammonia would. I have no idea. I'm gonna have to look into this though, because that's a really neat question. If anyone in the chat knows, please answer it. As a teacher, I feel like I just sometimes, I don't know, my husband makes fun of me for this, but sometimes I don't always know the answers to real world chemistry questions. But every time I see something that I don't know, it gives me an excuse to look it up and find out more. All right, on IG. So another question on IG. Does the AP exam count sig figs? No, if you're taking AP chemistry, there's going to be 1 point on the entire exam that's devoted for sig figs. So the safe bet is just to put 3 sig figs on everything. So you have like a plus or minus 1 sig fig tolerance. Rarely do you see anything with less than 2 sig figs or anything with more than 4. So 3 is a safe bet. All right, let's see. Looks like we had a question on TikTok. Yeah, do double bond covalent bonds count as Gen Chem? Because I need help with those. Yeah, let's do that. All right, let's switch this up, um, and let's talk covalent bonds. All right, so when it comes to covalent bonds, like understanding when to draw a double versus a triple bond, it is so tricky. It just takes a lot of practice with all those Lewis dot structures, but you need those because you're going to use those Lewis dot structures to then predict the molecular geometry. So let's just look at a very common compound that's going to have double bonds, CO2. So looking at this compound, if we wanted to draw the Lewis dot structure for this, first thing you want to do is just determine the total number of valence electrons in that molecule. So we're going to have 4 for carbon. This is just based on the column it's located in, or the group on the periodic table. If we move from left to right across our periodic table, starting with hydrogen, that's going to have 1. All the way over to your noble gases, those will have 8 valence electrons. All right, and then oxygen, I have 2 atoms of oxygen. Each one is going to have 6 valence electrons. So I have 6 times 2, that's 12, plus 4, that gives me 16 valence electrons. All right, so when drawing Lewis structures, you're going to find the total valence first. Next up, you're going to draw what we call a skeleton structure, where you just kind of guess how everything's going to come together. If your molecule contains carbon, carbon is going to need to form 4 bonds. It is going to be your central atom. Oxygen is going to need to form 2 bonds. So looking at this, I'm going to pretend I don't know that, and I'm going to just follow through with this. So first step, I counted the total valence. Second step, I drew a skeleton structure. Third step, I'm going to fill in all of those extra valence electrons on the outer atoms, making sure that everything obeys the octet rule. All right, so right now, oxygen only has 2 electrons, so I'm going to add in 6. All right, so now I'm going to double check my total and make sure everything matches up. So I have 2, 4, 6, 8, 10, 12, 14, 16. It looks good, right? But this is wrong. Okay, looking at carbon now, does carbon have the full octet? No. So what actually is happening, I can't leave this up, like it's going to hurt me to have that up on the screen. So basically what's happening, I'm going to draw it in a different way. So let's draw carbon's 4 valence electrons as X's, and oxygen's 6 valence electrons as dots. And if you can't see this, and let me know in the chat, and I'll try to adjust for next week too. It's definitely helpful to get your feedback as these sessions continue on. All right, so looking at this now, what I'm going to do is I'm going to combine these to form a bond. These are going to represent 2 shared electrons. That's easy enough, right? Now I'm going to look at these. See how each of our atoms has 1 electron just hanging out by itself? That's not going to happen. They want to party together, right? They want to form a bond. So we're going to combine these 2, and that's going to form a double bond. And then guess what? These 2 are also going to form a double bond. All right, so carbon dioxide is going to have 2 double bonds in the center. That was kind of like a roundabout way to show you how to do that. And unfortunately, with double and triple bonds, sometimes it is tricky like that. It just takes practice. So if you go through the process, find total valence, draw a skeleton structure, make sure everything obeys the octet rule, and then double check your count. If you are missing electrons, if you've drawn in too many electrons, chances are you're going to have double or triple bonds in that compound, and then you can adjust from there. I don't know if that was helpful. Hopefully that was helpful for double bonds, double covalent bonds. Other things you might need to know associated with these double bonds, right? As we increase the number of bonds, the bond length is going to decrease and the bond strength is going to increase. So a triple bond is going to be a lot shorter, but also a lot stronger than a single bond. All right. Okay. Yeah, so sorry, I keep missing. There's a lot of questions tonight. That's awesome. All right, so going back to our previous question, delta T is going to be the temperature, the final temperature. Yeah, so delta T is going to be the change in temperature. So anytime you see the symbol delta in chemistry, delta represents the change. All right, so delta T, this is what I mean by delta is the change. So it's always going to be your final minus your initial. So earlier we were doing the Gibbs free energy equation. Delta G equals delta H minus T delta S. So we have the change in enthalpy, the change in entropy but just that temperature that this is happening at. So this is only a single temperature. If we were looking at the change in temperature, you would have seen that triangle, that delta, representing the change in that. Yeah. All right. Let's see. Okay, and there was another question on TikTok. I don't understand rate laws. My test is tomorrow and I'm gonna fail. No, you're not. You're not gonna fail. All right, let's do some rate laws. Okay. And if you missed the initial one, we did look at a first order reaction right at the beginning of the session. Check out Chegg's YouTube. Normally the live is posted right away, so you can go back and jump back in and watch that again. All right, so let's see. So I don't understand rate laws. My question is tomorrow. What can we do? All right, let's just look at one. Okay, so the rate of a chemical reaction. And while I'm writing this on the board, feel free to keep asking those questions in the chat. Keep sending those in. It is so helpful to see what you guys are working on. Even if I don't get to all of the questions tonight, we will be back here next Monday, same time, same place. I will start with your question next week if I don't get to it this week. All right, so if the rate of a chemical reaction doubles, all right, so if the rate is 0.5 moles per liter at 20 . All right, we'll start simple with just a quick rate law question. So looking at this, again, hardest part is just like deciphering some of these questions. What do we know? What are we given in the problem? What do we need to find out? All right, so we know our rate is 0.5 moles per liter. We know our initial temperature is 20 and our final temperature is 50. We also are given that the rate doubles with every 10-degree temperature change. So first thing I would do with this one is you got to figure out how much that temperature changes, right? So we were just talking about delta T. Delta T is going to be 50 minus 20. That's 30 degrees. All right, that's with each 10-degree change, we expect it to double. How many times is this one going to double? 3 times, okay? So looking at this, I'm going to take 0.5 and I'm going to double that. And I'm going to double it again. I feel like this is a half-life problem to 4.0 moles per liter. All right, so that one's kind of an easy question. With a lot of the rate questions, you really just have to see what the question's asking. This one was kind of straightforward. Let's do one where we're looking at the reaction rates with respect to the concentrations of different reactants. All right. And the cool thing is I kind of anticipated that a lot of people will be working on rates this week. So I used Chegg's feature to just generate some practice problems. So if you have not checked out their new practice test option, it's really cool that they now have the capacity to do that for you. So all you have to do is type in a topic and they will generate 10 review questions for you with hints, with answers, with all of that. All right, so let's do another rate question. Let's see. Okay. And then after that, it looks like we're going to we'll be doing some IMF after that. So thank you, Anita, on TikTok. We'll be doing some IMF right after that. All right. So the reaction A plus B goes to C is second order with respect to A and zero order. Do you say zeroth? Do you say zero? It's a point of contention. With respect to B. Hardest part for me, right, is actually writing these questions out. If the initial, so we'll say if A naught is 0.5 molar and B is 8 And I think I'm giving the rate for this one too. Yeah, rate constant, sorry. All right, almost done writing this out. Sorry. Okay. So everyone's freaking out about rate laws and rate law expressions, things like that right now. So let's go ahead and look at this question. It's a pretty wordy question. I'm sorry it took me so long to write it down, but I want to give you a good example of the type of question that you might see tomorrow on your test. So let's look at this. So we know we have a reaction. It's a pretty simple reaction. It's second order with respect to A and 0th order with respect to B. What does that mean? That means the concentration of B does not impact our rate. So you know what we're going to do right away? We're going to cross that out. We don't need that information. That's like our excess reactant in a stoichiometry problem. We can just ignore it for now. All right, so we are also given our rate constant. What is the rate when the concentration of A is 0.1 molar? So when you're thinking about something that is second order, the rate is going to be equal to K times the concentration of A squared, all right, where our rate constant, that is equal to K. All right, so our rate constant is 0.2 inverse molar per second. That's how everything is changing with time with respect to that concentration of A. So what we want to do is we need to have that rate law expression memorized. So for that first order rate, right, we're going to have the, second order. This is second order. And what you need to do is you need to add up the overall order of that reaction, right? So in this case, we are second order with respect to A, 0th order with respect to B. Therefore, our overall rate is going to be second order. So what we're going to do is we're just going to remember our expression is 1 over our concentration minus 1 over that initial concentration, A naught, is equal to negative KT. When you are trying to memorize these, and I'll put them all up on the board so you can screenshot that, the good news is like this part always stays the same, right? We're just looking at 1 over A naught, right, versus the natural log of that versus, and also, how about I'll also draw the graph so you have those as well, because that's another thing that's helpful to memorize. So now it's just a matter of plugging everything in and trying to use some algebra to just solve for our missing, see, I've already lost, right, what we're trying to solve, right? What is the rate? So basically what we are trying to do is we're trying to figure out how much time we would need to have. No, see, we don't even need that. We just need to plug it into this equation here. So let's say I was trying to solve for the time, something like that, then I would actually use this expression. But this one is so simple that we only have to just use this. All right. So that's just a quick rate expression question. So okay. So basically all we'd have to do is we just have to say, okay, I'm going to take that 0.2 times my concentration of A squared. I don't know what that is off the top of my head. 0.1 squared times 0.2 gives me 0.002. All right, we're asked to find the rate. So we do need to figure out what our units would be with that. So just be careful with that as you're solving for that. So we have moles squared here. So we have molar squared, divided that. So this is just going to be molar per second. So just be careful with those units. When it comes to rates, it's all based on the order. If you do take the time to actually write out a chart, and how about I do that for you before we move on to IMF, it is super, super helpful. And let's say you're doing a different type of problem where you're given all of the concentrations of the reactants, and you're trying to figure out how, like, the order of the reaction. Just hold 2 values constant. So let's say you're looking at a chart with 3 different values for each of those things. Look at one situation where the concentration of A is changing, but concentration of B is consistent. Check to see how that's affecting the rate. And then you can work backwards to figure out, oh, that's quadrupling it. Okay, that's going to be second order with respect to that reactant. Oh, look, doubling that reactant did not change the rate at all. That's just going to be first order. All right, so let's just look at, so we have 0, first, second, We don't really, I mean, we could do third order. All right, so if something is 0th order, your rate is just going to be equal to K. All right, if it's first order, rate is such that rate constant with respect to whatever reaction it's first order and according to. Versus if it is second order, we just had an example where it was like second order with respect to A and 0th order with respect to B. You could also have a situation though, right, where it could be first order with respect to A and first order with respect to B. When you add those two together, still the overall reaction is going to be second order. All right, so that's pretty easy, right, just to know that. But where it gets tricky, right, is remembering those rate expressions. So if I have the concentration of A minus A naught, that would be negative KT for a 0th order reaction. If I am looking at a first order reaction, we have the natural log of A minus A naught. All right, versus second order, 1 over A minus A naught. And hopefully you will see a question where everything is graphed and you're asked to identify the rate based on that graph. Look for the linear line, okay? If you have just the concentration over time and that's linear, this is a 0th order reaction. If it's a natural log, it's a first order. If it is 1 over your reactant, that's going to be second order. So use these clues, memorize this so you have that when you sit down to take your test. All right. So a little bit about rates. I don't know if that helped. Hopefully that helped you prepare for your test tomorrow. But we're going to go ahead and switch gears and talk IMF. So it looks like we had a question from Anita on TikTok. Can you explain ion-dipole and dipole-dipole? Absolutely. So we are switching gears. We're going to talk some intermolecular forces. All right, we've been kind of everywhere tonight, but that's the goal of these sessions. So we still have 20 minutes left. Keep putting those questions in the chat. Whatever I don't get to tonight, I will answer next week. We are here weekly on Monday nights, and Chegg also has an organic session tomorrow. There's a stoichiometry session on Wednesdays, and then a Gen Chem session on Thursdays, another one. So they are here to help you this semester, help you survive. We're going to make it to, we're totally going to make it to spring break, right? We just got to keep pushing through. All right, so we're thinking IMF. I had a question just to go through ion-dipole versus dipole-dipole interactions. All right, so let's draw some particle diagrams. All right, thankfully the name will give you some clues with this. Ion-dipole. What's happening in this situation is I'm going to have some kind of ionic substance that's going to be dissolved into a polar solvent. So let's say I have water as my solvent. So I'm going to draw some water molecules. Let's see. And let's say I'm dissolving some salt into that water. What's going to happen with this, right? So when salt, so let's say I'm going to sprinkle some salt into the water. What's going to happen? Our salt is going to ionize. So we're going to have Na plus separating out and then Cl minus. So our chloride ions are going to interact with our positively charged hydrogen atoms. And our sodium ions, which are going to be positively charged, are going to interact with the negatively charged oxygen atom. So basically, it's just this idea that you have this ionic substance that's going to split apart into its positive and negatively charged ions. So the negative portion is going to interact with the positive portion, the positive ion, and the positively charged hydrogen atom is going to interact with the negative ions. That's not my best drawing. I apologize. But basically, in an ion-dipole situation, you have an ionic substance dissolved in a polar solvent. It's going to separate out. The positively charged ions are going to interact with the negatively charged portion of the polar molecule it's dissolved in, and then the positively charged ions will interact with the negatively charged portions. All right, that is the strongest of all of the intermolecular forces. We can also have a dipole-dipole interaction. So let's say I have HF. All right, so if I have hydrogen fluoride or hydrofluoric acid, hydrogen is going to be All right, let's just draw it like this. I don't know. I am not an artist. I apologize. So basically, let's think of this as a tug of war between those electrons, right? Fluorine is our most electronegative ion on the periodic table. It really, really wants that electron that's in that covalent bond. So it's going to pull all the electrons towards itself, leading fluorine to have a really negative, a partial negative charge. We just have an unequal distribution of those electrons. So what happens is if I have a bunch of HF, right? I'm going to have a bunch of portions where I'm going to have that positively charged hydrogen and that negatively charged fluorine. So we're just going to have this network developing again between all of those. And this is actually an example of a hydrogen bond. But basically, dipole-dipole interactions are just interactions between polar molecules. All right, so ion-dipole, I'm dissolving something ionic in a polar solvent. Dipole-dipole, I am looking at polar molecules. And the more polar the molecule, the stronger those interactions are going to be. All right, let's do like a sample problem because I feel like that was not the best drawing. So let's do something related to that. All right, it was just Valentine's Day last week. Let's talk. We could do some IMF with dopamine and adrenaline. How about we do that? All right, so I don't know that I really want to draw this, but we're going to do it. All right, so I have I'm going to change my mind before I do that. So basically what I want to do with IMF, if I'm asked to predict intermolecular forces that something is going to experience, I'm going to look at different portions. I'm going to determine whether it's a polar or nonpolar molecule. And if it is polar, do I have situations where I have hydrogen in a polar bond and then oxygen, nitrogen, or fluorine in another polar bond? Do I have a really electronegative element somewhere else? And that's where we're going to have hydrogen bonding. And I guess, we're going to go ahead and draw that. All right, so when we think Valentine's Day, you think dopamine, the feel-good chemical. So let's say I have dopamine. I'm going to go ahead and draw out the structure of this. If you are unfamiliar with organic, just kind of how we draw things in organic chemistry, chemists are lazy, right? So basically what we do, instead of actually indicating where we have carbons and hydrogens, we'll just have like intersections. So at each of these intersections, we're going to assume there's a carbon. And then not only that, we're also going to assume that that carbon needs 4 bonds. So this actually has 2 hydrogen atoms coming off of it as well. So when you go on to take Orgo, you will learn all of this. It's like learning a new language, but I promise it's not as bad as it looks. And it's kind of fun to try to decipher, right? Like where are all these carbons and whatnot. All right, so looking at this, I'll go ahead and draw in all of my hydrogens to help you guys out. All right, so this is the dopamine molecule. If I look at this and I want to determine what type of intermolecular forces it experiences, everything is going to experience London dispersion forces. Everything experiences. So London dispersion forces are just based on the random movement of electrons. So the greater the size of the molecule, the greater the polarizability of that electron cloud. Definitely a buzzword if you are in AP Chem. Just this idea that the more electrons you have, the stronger this force is going to be, right? Because if they're going to randomly congregate and you have more electrons, it's going to make a stronger dipole. All right, so everything experiences London dispersion forces where they just randomly end up in one spot, leaving a partial positive wherever they are not. So this is going to experience London dispersion forces. Is it going to experience ion-dipole forces? No, because it's not an ionic compound dissolved in a polar solvent. Okay, but now we can look at this and we need to decide, is this a polar molecule? So when we're trying to decide whether something is polar or nonpolar, we're looking for the differences in electronegativity. I will tell you oxygen versus hydrogen, that's going to be a polar bond. Okay, oxygen is very electronegative, so we have polar bonds here and here. I'll just try to highlight them. Also nitrogen to hydrogen, those are also going to be polar bonds. All right, so we do have polar bonds. Is this molecule symmetrical? Absolutely not. This is going to be a polar molecule. So therefore, we would experience dipole-dipole interactions. So now we need to take that one step further. The intermolecular force I have not spoken about is hydrogen bonding. So with hydrogen bonding, it's basically a specific dipole-dipole interaction, but it's a stronger interaction. It's always between hydrogen in a polar bond and a very electronegative atom, whether that's oxygen, nitrogen, or fluorine. So looking at this, I have a bunch of hydrogen atoms here. Those are not going to be sites for hydrogen bonding because the carbon to hydrogen bond is non-polar. Okay, so keep that in mind. Hydrogen to carbon is non-polar. Like write that down somewhere so you never make that mistake. This is a non-polar bond, but because I have hydrogen in this polar bond to oxygen and in this polar bond to nitrogen, I can have hydrogen bonding. So I would have 3 sites for hydrogen bonding. And let's say you're given 2 chemical formulas and you're asked to describe why one has a higher boiling point than the other. The number of hydrogen bonding sites, the strength of those intermolecular forces is going to impact all of those physical properties. So the more sites you have for hydrogen bonding, the stronger those intermolecular forces are going to be, and therefore the higher that boiling point is going to be. All right, just a little bit about IMF. Let's keep going. Let's see. So on Instagram, can you help with the difference between endo and exothermic reactions? Yes, absolutely. Use those prefixes, right? Endo means within. Exo, think exoskeleton. Think about all the insects, right? Exoskeleton, that's the outer skeleton. So if it is an exothermic reaction, we are giving that heat to the surroundings versus an endothermic, we are taking it, we are absorbing it. What you're going to look for is you're going to look for changes in those energy, the energy of the reactants, the products. If you have a negative enthalpy, energy has been lost, right? Your energy of your products is lower than that of the reactants. That's going to be an exothermic reaction. If you have a positive enthalpy, where the energy of your, I guess I should draw a reaction coordinate. All right, so let's say your reactants are here. You have your activation energy and your products end up here. This is a positive delta H. That's going to represent an endothermic reaction where energy is absorbed within. Okay, so again, if energy is absorbed, and the weird thing is when that energy is absorbed, your temperature decreases, right? An endothermic reaction is going to feel cold. An exothermic reaction is releasing a lot of heat, so it's going to feel very hot. So just a little bit on that. Looks like we have a question on resonance and then ionic versus covalent bonds. All right, so resonance. When something resonates, think about like a guitar string, right? If it is resonating, it's moving back and forth. Basically, that's what's happening with resonance. So resonance structures are multiple structures that are possible. So if you're thinking about Lewis structures, just multiple possibilities. And what we have to do is we have to then determine which one's going to be the best structure. So I think, let's see, try to think of something that displays resonance. We could just we'll do ozone. All right, so ozone is a weird structure. So we have 3 atoms of oxygen. We're going to have 18 valence electrons to worry about. We don't really have many options, right? Let's go ahead and just draw this. So we have 1, 2. And then we have like a weird situation where we have these like single electrons. So we are going to have a double bond like here. All right, so let's count this up. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Right, but could I technically have that double bond on the other side as well? Yeah, why not? So what this is, what when we draw resonance structures, we're just going to show the possible structures. This is not the best example because this double bond is just going to keep moving back and forth. But sometimes we'll have structures where let's say I have an example, like I have carbon on one side, I have sulfur on one side, nitrogen on the other, and I'm trying to figure out whether I have triple bonds or double bonds or single bonds. What you then have to do with resonance is you have to use formal charge to then figure out which structure is preferred. So resonance is just this idea that we're going to have multiple structures that are possible, right? Where just based on those valence electrons, and we have to figure out which one is the best based on the formal charge. You want the lowest formal charge, and you want the most electronegative atom in the molecule to carry that negative charge. If you're talking resonance in terms of orgo, come back tomorrow night. So there's a lot of resonance with organic chemistry. So if you're taking orgo, know that there's so much that goes into resonance past what you learn in Gen Chem. But it's kind of fun, honestly. It's like solving a puzzle. Yeah, awesome. And it looks like someone went ahead and put in the formal charge. This is my favorite. So with formal charge, if you were asked to find the formal charge of each atom, it's the valence electrons minus the dots minus the sticks. And what do I mean by that? This is just the lone pairs. And the sticks, those are your bonded electrons divided by 2. So basically, we're just counting. So let's say I want to find the formal charge of this oxygen atom. I would say that oxygen has 6 valence electrons. I have 4 lone pairs, or 4 dots, and I have 2 bonds to that. So this has a formal charge of 0. Versus this oxygen atom on this side, I have 6 valence minus the 4 lone pairs minus the 1 bond. This would have a formal charge of +1. All right, so that's how we'd actually calculate the formal charge. Yeah. Yeah, it looks like TikTok, you guys know your stuff. That's awesome. Yeah, all right. So I had another question on TikTok. Difference between an ionic and a covalent bond. Yeah, let's talk ionic versus covalent. These are all great questions. And, I had a lot of like thermo and acid-base chem prepped for tonight. So let me know what you want help with next week, and I'll make sure that I have questions ready for those so we can really dive in right away. All right, so ionic versus covalent bonds. All right, so I do not like how every chemistry class is just filled with really confusing terminology. So anytime I can give you a trick to break it down, I'm going to give that to you. So covalent bond, think about the word co. Someone is codependent, right? You are sharing. All right, so this is when electrons are shared. By 2 or more nonmetals. So let's say I had PCl5. This would represent a covalent bond. We'll go through naming in just a second in case you need that as well. Versus an ionic bond. In an ionic bond, you're going to have ions. So electrons are transferred between cation and anion. All right, so a lot of teachers will tell you it's okay, ionic bonds, you have just a metal and a nonmetal. And for the most part, that is true, but know that there are some exceptions, right? So you can have a polyatomic ion called ammonium, where ammonium is just nitrogen and 4 atoms of hydrogen. It's not a metal, right? But it still is classified as an ionic compound. All right, so in an ionic compound, electrons are transferred between the cation and the anion. So let's say I had Ca calcium phosphate. This would be an example of an ionic compound. So that's the difference between those. So if you're going through nomenclature right now, what you need to do right away is you need to be able to identify the difference between ionic versus covalent bonds. Easiest way to do that is to understand where we find our metals versus our nonmetals on our periodic table. Look at this wonky periodic table. All right, it will do. So if we're looking at this up to the staircase, these are all metals with the exception of hydrogen. Hydrogen is going to be our one lone nonmetal on the left side of the periodic table. And then on the far right side is where we have our nonmetals. All right, if you have 2 elements that are right next to each other, that represents a covalent molecule. So for example, PCl5, phosphorus and chlorine are just like 2 spaces away from each other on the periodic table. That's going to be a covalent compound versus calcium phosphate. We have calcium, our metal, bonded with phosphate. That's a polyatomic ion. Our anions are going to be nonmetals, right? But it's the transfer of electrons between calcium to phosphate that makes this the ionic compound. All right, if we want to name these, with covalent compounds, you are going to use prefixes to denote the number of atoms of each element that you have in that compound. And this is because we don't have ions to designate the charge. So what we need to know is we need to know how many atoms we have, because there are going to be multiple possibilities based on how those electrons are shared. So this would be known as phosphorus. You keep the name of the first element just as is, unless there are multiple atoms of it. So if I had 2 atoms of phosphorus, this would have to be diphosphorus. And then 5. It looks like someone had an answer. You're so close. Yeah. So if it was phosphorus Cl7, that would be hepta, but this is actually pentachloride. So knowing all those prefixes is really helpful. So it's going to be mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Yeah. So just be careful. So the ones that everyone gets confused, right? In every other class, 2 is bi, but in chemistry, it's di. Also, we're not going to use quad. It's going to be tetra for 4. So just be careful with that. And then once you learn prefixes, know that you do not use prefixes in ionic compounds. So for this one, we are going to keep the name of that first element the same. So this is calcium. And then we're just going to name it based on its polyatomic ion in this case. So this is going to be calcium phosphate. Let's say instead I had Ca3, that does not look like 3, Ca3P2. This would be calcium phosphide. So if we have what we call a monatomic ion, or an element that is just based on a single element, you just change the ending to IDE. So notice I am not worrying about using prefixes. Again, because this is an ionic compound, I just keep the name of the first element the same, and I change the ending of the second part to IDE. Let's say you have a transition metal, though. So let's say, I don't know, we'll do VCl5. So vanadium, we're still going to keep the name of that the same. But because vanadium is a transition metal, we don't know its charge. So we have to designate the charge with Roman numerals. So I tell my students, okay, don't worry about the charge yet. Just focus on the part of the name that you already know. We know this is vanadium. We know that chlorine is going to change to chloride. And now I can work backwards. So I need to find the charge of the negative portion because the metal has to be equal and opposite to that. So it's kind of easy. Chlorine is just -1. So basically I have -1 times 5. It gives me a net negative of -5. That means vanadium has to be +5. If you have learned with this process, if you have learned to do the crisscross method, sometimes you can do the reverse crisscross and sometimes it works. Doesn't always work though, so just be careful. In this case, it does. So just be careful with that. All right, let's see. Okay. Yeah, so it looks like TikTok is you guys are on it tonight. Yeah, so this is just a Gen Chem session. So it's just inorganic. It is basically just Gen Chem, which is a lot of inorganic, but I'm not like I'm not really getting into actual inorganic chem. I think right now Chegg is doing organic sessions, 2 Gen Chem sessions, and then like a stoic session, which again is Gen Chem. But if that's something you all would like to see, let us know. Yeah. All right. Any other questions? We have like 30 seconds left. Thank you all for being here tonight. It was very random tonight. I hope it was helpful. Please let us know. And I'll be jumping in the chat right after this to see what I missed. So if I ever miss anything, the plan is to come back next